In this video, I'm basically doing a re-recording of audio for Cholesky factorization. All of my old videos have lost sound quality due to some YouTube updates, so I apologize for that. And so let's get started with Cholesky factorization. So the first thing with Cholesky factorization is that we will have A should be a matrix which is symmetric, positive, definite. So what does it mean for a matrix to be symmetric, positive, definite? Well, hopefully you guys understand symmetry, which is that A transpose A is equal to A. And positive definite basically means that for any x other than 0, x transpose AX will be greater than 0. And for x equals to 0, x transpose AX will be 0. Now, if instead of greater than 0, it was greater than or equal to 0, then it would basically be a semi-positive definite matrix. That is, x transpose AX is greater than or equal to 0. Here in this old video, I'm basically explaining the symmetry part. So I'm saying A is equal to A transpose, and if the matrix is complex instead of real, in that case it will be A is equal to the conjugate of A and transposed, so we call that a Hermitian matrix. So now that we understand what it means for A to be a symmetric, positive, definite matrix, let's look at the Cholesky factorization. The Cholesky factorization basically says that we can factor this matrix A into two other matrices, a lower triangular matrix and its transpose. So A can be represented as L, which is a lower triangular matrix, and L transpose, the product of L and L transpose. So now that we understand what the Cholesky factorization is, let's look at how we might use it to solve an equation like AX equals B, which is a typical problem in linear algebra. You have a matrix A, you have a collection of x's, which result in a collection of b's. So we factor A into L, L transpose, and we get L, L transpose X is equal to B. And let's relabel L transpose X as a variable Y. So this equation becomes Ly equals B. Now, this is a simpler equation to solve because L is a lower triangular matrix. So we can solve Ly equals B for Y. And then once we know Y, we have a upper triangular matrix L transpose, and we can solve for X. So this simplifies the problem of solving AX equals B. So now that we have seen how to use this Cholesky factorization, we will look at the third part, which is how do we derive this Cholesky factorization or get to it. So we know that for a matrix A, which is symmetric, positive, definite, we have another factorization called the LDU factorization, which basically says that we can take this symmetric matrix and factor it into a lower matrix, a diagonal, and its upper matrix. And these are positive matrices, since we are positive definite. So next, what we can do for this is to say that A is equal to A transpose because of symmetry. So LDU is equal to U transpose D transpose L transpose, That's what we reverse the order of matrices when we transpose their product. And now that we have A equals A transpose, or LDU equals U transpose, D transpose, L transpose, we can rewrite the L transpose part as just U. So the lower side transposed, and it's symmetric, so it's just U. So this becomes U transpose D U. And we can factor D into its square roots. So we can say, so D square root of D times the square root of D is just D. So we can rewrite this as U transpose square root of D times square root of D times U. And as you can see, the square root of D, since D is a diagonal matrix, you can actually just move that out and around. So this is really the same thing as writing square root of D times U transpose times square root of D times U. And you effectively have a lower matrix and an upper matrix being multiplied. So we have essentially factored A into L transpose and L. So this is how we derive the Cholesky factorization using the LDU factorization.